Alright, so in this video I'm going to be going over electrochemical cells or batteries. They're also known as voltaic cells or galvanic cells. So if you see any of these terms, we're really referring to a battery. And if you guys remember, there was an episode in Breaking Bad where they were stranded out in the desert and they actually had to create electrical energy. And they did it with this. This is exactly what they did. They made a battery with stuff they just happened to have around the RV. All right, so an electrochemical cell is an apparatus. So it's a system or a device that we build to generate electrical energy. So it makes electrical energy from a spontaneous reduction oxidation reaction. So if it's a spontaneous reaction, we can basically use that to generate energy. So what we do is we take two half cells and we connect them together. So the half cells have to have different electrical potentials. So in one half cell, you'll have a more positive electric potential, and the other one will be less than that, usually negative. So when we do that, we connect the two half cells together. So it looks kind of like this. So remember, a half cell is a piece of metal in a solution of its own ions, so maybe copper in a copper solution. So what we'll do is we'll have two half cells together with different metals, and one will have a more positive electric potential, and then one usually will be negative. But anyway, what we do is we will connect it with a wire, and then we also connect it with a cell bridge, which I will explain the importance of that in a minute. But basically, because we connect them together, it generates electrical energy because there's a spontaneous reaction that's going to happen. And electrical energy is basically the movement of electrons. So because one has a higher electric potential, we have the ability to move those electrons to the other cell. So there are two types of electrodes. So we're going to have different pieces of metal. One will be the anode and one will be the cathode. The cathode is going to be where reduction happens. Okay, so the cathode will be where electrons are gained. Remember, it's counterintuitive. It's always the opposite of what you think it should be. And the anode is where oxidation happens. So that's where electrons are lost. So basically, from one of the metals, electrons are removed, and it moves through this wire, and then it goes into the other cell, and then the electrons will be gained by the ions that are in this solution. Oh, and please make sure you remember the cathode is where reduction happens, the anode is where oxidation happens. And I remember it by the saying red cat, reduction for red, but yeah, red cat. Okay, so now this is basically how it works. The electrons will flow through the wire and travel to the more positive half cell. So in this case, if we look at this particular cell that we have right here, if we look at this particular cell, we have copper and we have zinc. The two half cells are connected with a high resistance voltmeter, and that's important. It needs to be high resistance so that this does not interfere with the electron flow. All right, so copper has an electric potential of, let's see, this 0.34. And the electric potential here is going to be negative 0.76. Well, this is more positive. So since this actually has a more positive value, electrons are attracted to positive things. So electrons will be removed from this metal. So this is the metal that we have, the zinc electrode. So we're going to remove those electrons. And when we do that, we're going to create zinc ions. So when I remove those electrons, zinc ions will actually be deposited into this little cell. The electrons will start to move through the wire, will move to this copper, and then because we've got electrons here, these copper ions are actually attracted to the electrons, and then we'll gain those electrons, and then we'll get more copper solid on the electrode. So that's basically what happens. The electrons will flow to the more positive electric potential. Electrons will be removed from this one piece of metal, will move through the wire, go to the other cell, and then the electrons will be added to the ions that are actually in the solution already. And when this happens, the salt bridge is going to alleviate some charge buildup, which I'll talk about in just a second. But this right here is called a cell diagram. Okay, so this is a drawing of the apparatus. Okay, this is a drawing. This is a cell diagram. Okay, the cell diagram basically shows you the reaction that's happening. So in the reaction, zinc solid is turned into zinc 2+, and then the double line here represents the salt bridge, essentially, so the connector. And then what we do on the other cell is we take the copper ions and we make copper solid. So it shows you the reaction here. So basically, I have zinc in one cell. I remove the electrons to make zinc with a +2. And then in the other cell, I take the copper 2+, and then I make copper solid. It's just showing you, it's another way to represent the reaction that's happening. All right, so why do we need a salt bridge? Well, a salt bridge is very important because it allows ions, not electrons, to travel between the two half cells. And it completes the circuit and allows there not to be an overabundance of ions in one cell. So a salt bridge is usually a piece of filter paper. Sometimes it's a U-tube. It has an ionic solution in it. And that ionic solution is not supposed to interfere with the reaction that you have. Basically, you just want to make sure your solution that you put into the U-tube or the filter paper does not make a precipitate with any of the ions. So a good example of this would be if we're doing something with silver ions, well, silver ions will react to potassium chloride to make silver chloride as a precipitate. Now, usually a good thing would be maybe like potassium nitrate, because, well, nitrate is soluble with everything. So anything with nitrate is going to be a good option, or sodium nitrate would be a very good option because sodium doesn't make a precipitate with anything, and neither does nitrate. Oh, so when we look at the salt bridge, though, ions are traveling through it, not electrons. So basically, when you're, go back. Okay, when we look at this cell right here, well, zinc, the electrons are being removed from it, so we're creating zinc 2+ in this solution. Well, as the reaction keeps going and going and going, I'm getting more and more zinc plus here. And that becomes a problem because now I've got more ions in this solution than this one. So what the salt bridge does is it connects them together, and then the ions will start to flow through. Into the other half cell to make up for that difference. Okay, so to make a cell diagram, and remember this is not the same thing as a drawing of the actual apparatus. The reduced species is going to be placed on the right. So we're always going to start off with the cathode. So we need to figure out what's being reduced and what's being oxidized. And we're going to know that by looking at our reduction electric potential table. Remember, the more positive the value, the more likely it is to be reduced. So the more positive or the higher the number, that one, the one that has the higher electric potential, is reduced. The other one will be oxidized. The vertical line, just one single vertical line, represents the different phases in the half cell. The double vertical line will represent the salt bridge. And then if we happen to have different species in the same phase, we're going to separate it out with a comma like this. Now, if we have an inert conductor, basically if you have something that's a gas, fluorine, hydrogen, oxygen, any of those items, you have to include platinum because that is actually what's going to allow the reaction to happen. So it would look something like this. So instead of just having the species that's reduced and the ion, you're also going to include your inert conductor. If you do have a species like that, like hydrogen, fluorine, those things, they're diatomic. So we're going to include a 1/2 to make them challenged, or to make them balanced.